Okay, we were talking about probability, and so we're going to go ahead and continue our discussion. We're going to focus on games of chance here, basically using a traditional 52-card deck. Yes, there are 52 cards in a deck. I have had students who are unfamiliar with playing cards. I'm not sure how that happens, but there are 52 cards in a traditional deck. There are 4 suits. There are 13 cards per suit. It goes from ace to king. There are 3 face cards, jack, queen, king. Depending on the game that you're playing, the ace can either be used as a 1 or as a 14. When we say 14, we mean that it can go with the face cards jack, queen, and king, but it is not a face card. Okay, it is a numeral card. Okay. For the purposes of this exercise and any exercise that we're going to do, our sample set, or I should say sample space, will be 52 cards, all 52 cards. And so what we're going to do is take those cards and we're going to deal with some probabilities. A single playing card is drawn at random from an ordinary 52-card deck. Find the probability of drawing a queen. So I need to know what the event is, right? For this one, for part A, the event is going to be equal to the 4 queens that are in the deck. Okay? We can have a queen of hearts. We can have a queen of diamonds. We can have a queen of spades. It's not my best one. And we can have a queen of clubs. Didn't mean to go off at an angle there. That's our event, okay? So what is our probability? Remember that the probability of the event is equal to the number in the event space divided by the number in the sample space. There are 4 cards in the event space. There are 52 cards in the sample space. So we simply say 4 over 52. We must always reduce these things. You know that fractions have to be reduced, which means the probability of drawing a queen is 1 in 13. Notice that I have left it as a fraction. Unless otherwise stated, you will leave it as a fraction. Do not convert it to a decimal. But if the problem says enter a decimal, then you would just simply use your calculator and divide it out. Okay? So now let's look at part B. Part B is the probability of drawing a diamond. Well, I know that when we look at the probability of drawing a card that is a diamond, that means that I'm looking at the number in the event divided by the number in the sample space. How many diamonds are there? There are 13 because there are 13 cards per suit. So that means that this will be equal to 13 over 52. Once again, reduce. It is simply 1/4. Now what about the probability of drawing a red card? When we say the probability of drawing a red card in this particular instance, that means it's either a diamond or a heart. So once again, we want to look at the number in the event space divided by the number in the sample space. Since I'm talking about 26 cards total, it'll be 26 out of 52, which means that I have a 1 in 2 chance of drawing it. Or I should say I have a probability of 1 over 2. Many people are tempted, and they do say, you got a 50% chance of drawing a red card. And that is an erroneous statement. Okay, when you start talking percents, you're talking odds. Odds are completely different than probabilities. Okay, you have a 50-50 chance of drawing. That's okay, but you're not going to write it as a probability. Okay, odds are different than probabilities, and we'll talk about that too. Now, does anybody have any questions about what I just did? Okay, for any event E, you will read that as 0 is less than or equal to the probability of E less than or equal to 1. This is a much nicer way of saying it for everybody to understand. All probability events will be between 0 and 1 inclusive. The probability of E equal to 0, it will not occur. Not going to happen. If you have a probability that's 0, it can't happen or it won't happen. If the probability is equal to 1, it must occur. You have no choice. It will occur. For example, if we're rolling a 6-sided die, what's the probability that I will get a 1, a 2, a 3, a 4, a 5, or a 6? 1, because I'm going to roll it, and I've never seen a die on a flat, smooth surface land on its point and just sit there, unless you're in the movie Inception, right? Okay. So, what does that mean for me? Well, it means I can take all this information and I can find probabilities of events occurring. We're going to look at example number 8 here. The table gives a frequency of households having an average monthly electric bill in various dollar amounts from a portion of the respondents of the 2007 American Community Survey conducted by the U.S. Census Bureau. This is just electric. Most major cities, their utility companies are split up into multiple various entities. I mean, Decatur, it's all one monopoly. So when people talk about their utility bill in Decatur, they're talking about the whole thing, not necessarily focusing on the electric bill. This is just the electric bill portion, okay? And it gives me, 7 categories. We have 0 to 99, 0 to 49.99, 50 to 99.99, and so on. These are the frequencies with which those occur. And if we add all this together, we'll know how many people responded to this thing. And if we do that, we will find that 1,000 people responded, which is a good thing, right? Because I have a lot of data here. You will find that when we're discussing statistics, that more data is good. Too much is bad, but the more you have, the clearer a picture you're going to get. So that being said, I want to look at checkpoint 8 and says, find from the data given in example 8, find a probability that a household has an electric bill less than $200. Well, that means that I have to look at my categories here for those bills that are less than $200. Which means that I'm going to add these 4 values together. Okay? The reason I'm going to do that is because each one of these represents the number in the given set. Okay? So 270 is the number in that set from 0 to 49.99. So I need all 4 of those things to get this, because this is what I'm looking for. The number that the utility bill or electric bill is less than 200, which means that it's going to be equal to 270 plus 253 plus 203 plus 112. Okay, add those together and you will come up with 838. Now remember, the probability is given by what? The probability of an event is equal to the number in the event space divided by the number in the sample space. What's my sample space number for this one? It's 1,000, okay? This is the number in the sample space, and this is the number in the event right here. So that means this is going to be equal to 838 over 1,000. Okay. Now let's examine this for a moment. That is not a simplified fraction, right? I can simplify it by dividing, well, both of them are divisible by 2, right? So I'm going to go ahead and simplify this fraction down to the following. Oops. That's the probability that if I pick an electric bill at random, it will be less than $200. Does that really tell you much? Not really. If we go ahead and convert it to a decimal now, and this is one of those times where you would want to, that's your probability. This right here tells you a lot. What's the likelihood that if I reach into a bin with all these electric bills and draw one out at random, that it will be less than $200? Well, that's a pretty high probability. So it's pretty likely that I'm going to grab one that's $200. Does that mean that or less than $200? Does that mean that I will? No. Does it mean that every single time I do it, I'm going to get one that's less than $200? No. This right here is a calculated probability, but it's theoretical. Okay? The only way to prove that this is true is to go ahead and draw 419 bills out of 500, or draw 838 bills out of 1,000, and they are all less than $200. So probabilities are not necessarily something that is going to guarantee an occurrence. How many of you guys pay attention to the weather on a daily or semi-daily basis? Nobody? You guys don't watch the weather? Never watch the Weather Channel? Never look at your phone to see what the weather is going to be? Come on. Everybody in here has looked at the weather. And that's all probabilities. And that's why sometimes they're right and sometimes they're wrong. It's based upon historical data, and it's based upon certain weather readings that they take, and then they put it into a mathematical model in the computer, and the computer spits out, well, there's a 60% chance of rain. Does that mean that it's going to rain 60% of the day? No. It means that at any given moment in the day, there is a 60% chance that it will be raining. So when you look at the weather and it says 60% chance of rain, do you believe that it's going to rain at some point during that day? There is a high likelihood that it will. Does that mean that it's going to rain in the particular spot that you're in? No, because we know that weather does not always blanket the place that we're talking about. It could be raining across the river, and it could be dry over here. And that happens all the time. Okay, so let's talk about properties of probability. We're going to let S be a sample space consisting of n distinct outcomes. In the case of the die, how many distinct outcomes are there? There are 6, okay? We're going to label them as S sub 1, S sub 2, S sub 3, S sub 4, all the way up to S sub n, where n is the number of possibilities. Okay, so n is the number of possibilities. An acceptable probability assignment consists of assigning to each outcome, S sub I, a number P sub I. Now, you don't have to write all this down because I'm going to kind of explain it so it's not all in mathematical jargon, okay? And this is basically what we're looking at, is if I have a sample space, okay, that's my sample space. I can break this up into 6 unique subspaces. There, that's the word I was looking for. And then I can create probabilities associated with each one of those. Notice that I've got these subscripts here. So the probability P sub 1, and I'm going to use a little p for this, not a big P. The probability P sub 1 will be equal to, and I'm going to write this as the number in the event space divided by the number in the sample space. Notice that I have a subscript here, which means that it's a unique event, this one right here. Since there's no subscript there, that's the entire space. And that's going to simply be equal to 1 over 6. And I'm going to have that for each one of my subspaces, which means that I can go ahead, let's get rid of this. I can go ahead and list them all. P sub 2 will be equal to 1 over 6. P sub 3 will be 1 over 6. P sub 4 will be 1 over 6. P sub 5 will be 1 over 6. And P sub 6 will be equal to 1 over 6. What this whole theorem right here is saying is that if I take all the possibilities of the probabilities, so all the probabilities in the sample space, they will add to 1. If they do not add to 1, you've done something wrong, and or it's not a true representation of a sample space and all of the probabilities. So that means that P sub 1, well, let me do this. This right here means that I can take 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, add them together and get 6 over 6, which is equal to 1. Okay? Those are your properties of probability. Your probabilities must be between 0 and 1 inclusive. In a sample space, if you look at each one of the individual probabilities associated with the results in the sample space, when I add them together, I will get 1. Okay? Any questions? Okay.